I'm Han Junguo from Huawei OS kernel team. Today I would like to talk about the MPAM. So I'm not going to talk about the MPAM details implementation, but talking about the deploying the MPAM on the cloud using the server. So here's the background. So we are talking about the cloud. That we're running virtual machines and containers on top of that. But for the data center resource utilization, it's the typically average between 10 and 30%. So we adopting the technology of the co-location, especially with the resource isolation mechanism, can reduce the optional cost to increase the utilization efficiency. But with the cyclicals increases, especially with many core system, so such as ARM, there's a lot of cores. For example, with more than 200 cores, there still some performance decrease. So, for example, here's the chart shows that we're running a MyCircle TP99 test on more than 300 CPU system. So this shows that the TP99 interface rate, and here is the number of the containers running. So we use the 2 CPUs with 4 GB memory. So we can see that this one is the customer acceptable latency jitter. But if with the containers numbers increased, for example, for about 32 containers, the latency jitter is more than 10%. So this, which means that after this is not usable for the customer. Yeah. So what's the problem? Who is lowering the co-location performance? So we are talking about the, we're talking a lot about the noise neighbor, right? But so what's those noise from the OS point of view? So I think there's 2 major ones from the operating system point of view. The first one is the contention from the OS level. So such as logs, for example, secret mutex, kernel NFS, read-write semaphore, something like that. And also, we have some big memory on the NUMA node. So there is a long IO list to manage the memory. So there's a lot of noise on that. The second one is the contention from the hardware. For example, the memory bandwidth, cache, and the IO sharing. So there is a simple diagram to that. This is the kernel level. So there's a lot of contention from the shared resources for the kernel side. And another one is from the hardware side. So shared resource for the hardware, for the memory bandwidth, cache, and the IO. Okay, so today I will talk about the hardware contention. So the hardware contention is the key point to the co-location utilization. So we have a test for the Kunpeng 920 server. So the blue one is we are running the MLC, and the orange one is the omelet. So you can see that if we run it, that the cache contention is really a lot, and that one is with the isolation. You can see that the no contention. So from the test case show side, there is a lot of cache contention, and in the real workload use cases. So plus the memory contention is will reduce a lot of the IPC, so instruction per cycle, for more than 20. So what do we need that? We need the isolation. So from the CPU point of view, we need isolation for the cache and the memory bandwidth and for the IO. But the isolation is is not enough. So I think with 3 major things we need. The first one is monitor and provide application demands for the shared resources. The second one, we need to analyze the performance impacts of shared resource contention. And the last one, so we have monitors, we have performance analysis, and then we need to provide the resource allocation and the isolation mechanism to ensure the performance. Okay, so what we got from the ARM architecture? We got MPAM. So I think that a lot of people are knowing that. So we just to say that we have 3 resources which can monitor under isolation. The first one is the last level cache, but also we can also do something on the level 2 cache. For example, if we have the SMT. So 2 SMTs can, to do some partition and the isolation from the level 2 cache. And the second one is the level 3 cache, it's the last level cache, and the memory bundle wise, and the IOs from the SMU. So the MPAM mechanism enables the user-controlled service flow isolation by tagging the request with the part ID and the performance monitor group at the CPU and the SMU originals. Yeah. So that means that we can control the memory bundle wise, level 2 cache, level 3 cache, and the IO. That is from the hardware point of view. So what we did from the software. So I'm a kernel guy, so I'm working on the kernel side. So from the OS point of view, the kernel have 2 layers. The first layer is the MPAM driver. The driver is talking to the hardware. So such as when we have some isolation with the resources, so we need the MPAM context switch, which talk to the register and do some partitioning. And the first one, we need some monitor to say, okay, how many caches we need. And the second major layer is the kernel resource control framework, which means that it talk to the user space. We need to provide the interface to the user space to let the user space to configure the resources we need. So there's a major 2 layers of from the kernel side. And for now, there's some introduction yesterday about the MPAM progress. And the resource control is almost in the main line. So yeah, that's really good news. There's a lot of work from James. Okay, so for now, I will share some test result we're doing. So first, I need to introduce the hardware and the software. The hardware, we're using the Kunpeng ARM20. So and the software, we're running the OpenEULA. So you can see that with the 920, we have the about 16 cores per node. And for the last level cache, we have 16 last level cache monitors and the controllers for the MPAM. And for each memory controller and the DRAM controller, we have 4 monitors and controllers. Yeah. And I think there's some features that compared to x86, the MPAM, some useful features. For example, for the memory bundle wise, the minimal bundle wise, and that's actually is really useful. For x86, we just okay, we have only the maximum bundle wise, but for the minimal, for example, if I is really a latency critical workload running on container or VM, okay, I can see that we can see the memory bundle wise minimal to that container, which means that okay, I'm the king of the world. I can use at least 80% or something like that, and the rest of which can be used by others. So that's from our point of view, and when we deploy the MPAM in the real use cases, and then the memory bundle wise for the minimal bundle wise is really a useful feature. And the other things such as priority and the last level queues control with the no contiguous allocation of the cacheways across the part IDs. That's compared to the x86. Yeah, the MPAM have some features really useful. Yeah. So for the software, we adding some patches on top of James Moore's MPatch sites, and the OpenEuler provides full support for the MPAM features. Yeah. Okay, with the hardware introduced and the software we are running, so here's some interesting test results. The first one is the benchmark test. Yeah, so which shows how the noise and how to contain the noise. Sorry, there's a there's a bug here. Actually, the x coordinate means the times when we are running, but the x coordinate is the instruction per cycles. Sorry. So we're running the omelette without the contention. So we can see that the instruction per second is about 0.5, and the time to finish the test is about 150 seconds. Yeah, but so okay, we're adding some noise. We're running the omelette and with the stress NG. So that is memory hungry and there's a lot of contentions. So we can see that the IPC drops a lot compared to this one. Yeah, and it's nearly about 0.2, and the time to finish the test, it's increased, double, more than double, right? So we're adding some MPAM features on top of that. The first one, we only with the cache isolation only, So you can see that the IPC increased a little bit, and we just to isolate the stress NG from the cache. So and the time to finish that is about 300 seconds, and yeah, it's a little bit better. So. And then we switch to the memory bandwidth isolation, and you can see that the IPC is a little bit better than with the cache isolation. Yeah, and the time to finish this test result is better than this one, than the cache isolation only. Okay, so, then we adding both the cache and the memory bandwidth isolation to the stress test. So it seems that it's the same as the memory bandwidth. Yeah. So this is the benchmark test. Yeah, and which shows that it works, right? Yeah. So we are switching to some real use cases. So actually, we test from the customer there's some collocation of the workload, such as MySQL, Redis, and something like that. So MySQL is a memory intensive and latency sensitive workload, and so we're doing a test case with MySQL, and is a batch workload with is a benchmark. It's a BW memory, so it's just a simulation as the Spark. Yeah. So actually, in the internet companies, the Spark is kind of a batched workload, and for the MySQL, the Redis is a latency critical workload. So here we are running the MySQL in a container with 16 cores. Yeah, here's the performance. The transaction per minute. Yeah. So if with the co-location, the performance is more than it's here, right? So then we just adding the BW memory to do some as the neighbor noise. So we can see that the performance drop is more than 20%. And so we are adding. We to isolate the BMW with only, okay, you can use only 4 ways of the cache, so limit that. Then we can, the performance, it's increased. And then with the memory bundle wise only, you see that, okay, you can use only 10% of the memory bundle wise. And it's a little bit better. And the last, to say that, okay, we can just with the cache and the memory, both the cache and the memory bundle wise limit, and the performance even better. So actually, this is a little bit drop compared to the original one. So actually, the MPAM and it's really it works. For the real workload. Okay, so here's the interference rate. I mean, it's the same as this one. So not only for the performance, but only to say, okay, the customer can accept the data recency, right? So we can see that if we co-location without the isolation, the interference rate is too high, and the customer cannot accept that. It's about 20%, more than 20%, and with the cache limit, it's less than 10%, and with the co-location with both the cache and the memory limit, it seems pretty good. So that's the test result for the real use cases. Okay, here's the final slide, and so MPAM is is really a useful feature for cloud service, especially for workload co-location. And the second one is that so when for the real use cases, the memory bundle wise isolation can be applied for more use cases, and which means that more useful, especially for the cloud service. And if for a lot of use cases, if you apply it with both the memory and the cache isolation, we can achieve a greater performance or the optimization. Okay, thank you. Any questions?
Sorry, it's not a technical question. Just maybe I missed the details over there. So, are you using ARM Neoverse reference design, or is it your own SOC design? Maybe I missed that part for Kunpeng.
So so we are adding some patches on top of the James Moore's hardware.
Uh-huh.
The core.
Uh-huh.
It's ours. Is the key.
It's ours.
Okay. Okay.
Not the universe.
Okay. Okay.
Yeah.
That was the question. Sorry.
Yeah, it's already supported on the mainland kernel.
Is that the wiki chips?
I think so.
Yeah, I saw the wiki. No, it's released 15 hours ago, so there's no problem. So I was just checking. I was just trying to be sure. Okay.
Yeah.
Thank you.
So how does a customer actually tune the parameters? Is it, at the moment, is it a very static process where they take a workload, fiddle with it, basically do parameter search? Or do we have any attempt to automate it using, I don't know, the PMUs to guess what the right settings are?
Both. Yeah, both.
Short answer.
So
fair enough.
So for now, so when we introduce the MPAM for the customer, so a lot of them, is as in manual. Yeah, but for now we're trying to do that on the, we have so actually we have monitors, right? Yeah, and we do some automatic to monitor the cache where what the application is and the memory bundle wise. Actually, it works because the monitor is not only used for the MPAM to isolation, but if we just not to use isolation for the MPAM feature, we just to monitor the applications memory bundle wise and the cache usage. We can do some performance tuning. Yeah.
the MPAM only monitor the memory and cache. How about the bandwidth of some accelerator?
Good question. So actually, they suppose the SMU. But on this one, on the Kunpeng 920, it's not supported. But for the new one, it's supposed I/O bundle-wise limit. Yeah. So actually, James Moore's passage, including that, is not in upstream. So we do some work on top of James' passage. There's some bugs. We adding some bug fix on top of that, which is available in the OpenEuler kernel version. Yeah.
We sent them to James too.
Yeah.
So the implementation, which you mentioned, like James Moore's patches, is it able to auto-adjust the bandwidth? So you have to statically basically establish.
That's user space 4.
Okay.
James is just sorry, you should answer.
Yeah, please.
James is obviously just dealing with the kernel side of things. You obviously need other tooling, which Hanjin, I guess.
Yeah, other tools. So actually, there is other tools in the user space. Yeah.
Okay. And do you plan to extend it to support virtualization?
Virtualization. So we don't find not much useful use cases. Yeah, because we do some isolation for the co-location, the use cases. Some of them, most of them use containers. But for the VMs, there is not much bigger VMs, and running a lot of workload inside the VM. Lot of actually the customer they're running, so actually they're running a single or workload, such as we're just running my circle inside the VM. So there's not much co-location inside the VM.
Okay.
Yeah, but from the experience, I just from the customer. Yeah, I'm not sure other use case for that. Yeah, so we actually for now we don't support the MPAM inside the VM. Yeah.
I'm curious. Has anyone else built the hardware? Is it willing to say they did for the virtualization?
We also do not do that.
It's in the spec. But
yeah, I think it's come from the real use cases. If there is a real use case, we can do that. Yeah. Okay. Thank you. Yeah. Thank you.